We're going to shift gears a little bit today and talk about energy. Now, this is still in the unit that we call dynamics, which is the study of motion with regard to what causes that motion, i.e. forces. And the reason we're doing it, though, with this dynamics unit is because really it's forces that result in energy. We're going to define work and do some work with work tomorrow. But for the time being, you just need to know that it's forces that cause work. And work is what results in energy. So energy is really a part of this unit, dynamics. It's just going to seem a little bit different, that's all. We define energy in general as the ability to do work. The ability to do work. Sometimes work is being done. Sometimes work is not being done, but energy just gives us the ability to do work down the road. In other words, it stores it for the future. We've defined two types of energy. One type is called potential energy, kinetic energy. Kinetic energy is the energy of motion. Energy of motion is when work is being done already. Work is being done now. Something is moving. Right? If something is moving, work is being done. Potential energy, on the other hand, is stored energy. This means that work can be done, but work isn't being done right now. As I hold the board marker about 2 meters above the ground right now, work isn't being done on this board marker right now, but there's the potential for work to be done. If I drop the board marker, then gravity will accelerate this board marker. So it goes from a stored energy where we have the ability to do something to kinetic energy where something is being done now as it moves down. Does that make sense? So kinetic energy and potential energy. Now, we're going to break potential energy down into several categories, several different subcategories. Kinetic energy, we usually just say kinetic is kinetic no matter what the scale. The kinetic energy of a car traveling down the road, the kinetic energy of a planet traveling around the sun, the kinetic energy of an electron traveling around the nucleus of the atom. Kinetic energy is kinetic energy. But potential energy can be broken down into several types of potential energy. We can store energy in a number of different ways. What's one type of potential energy? What's one way that we can store energy? A way that you learned in Science 10. We just talked about it a second ago, although we didn't name it. Enrique? Yeah, gravitational potential energy is one type of potential energy. And gravitational potential energy is the energy stored in an object due to its height. The higher something is above the ground, the more potential energy it has, right? Think about that. Okay, if I am on the third floor of a building with a rock, okay, that rock has a certain amount of potential energy because it's on the third floor above the ground. If I'm on the 100th floor of a building with the same rock, then it has more potential energy because it has more ability to do work. If I drop the rock from the third floor of a building, okay, I might put a dent in a car if it happens to hit a car on the ground. If I drop it from the 100th floor of a building, okay, it might go right through the hood of the car if I drop it from the 100th floor of a building. Why? Because it's going a lot faster. Why? Because it was on the 100th floor, it stored a lot more energy. It gave it the ability to do more work. What's another type of potential energy? Where's another place that we can store energy, Colby? Chemical potential energy. Now, we're not going to talk a lot about chemical potential energy in Physics 20. Clearly, that would be more of a chemistry thing than a physics thing. But you're absolutely right. We store energy in gasoline. And how does your car end up going forward? It burns gasoline. There's chemical potential energy stored in the gasoline. In fact, there's chemical potential energy stored in food. That's how we end up going forward as well. It looks a lot different, right, than when it's stored in gasoline, but it's really fundamentally the same thing. Energy stored, the ability to do something, the ability to make the car move, the ability to make us move, stored in chemicals, okay, chemical potential energy. Any other kinds of potential energy? There's got to be something besides these two. Yep. Yes, we're going to say elastic potential energy. I'm going to put spring in there as well because you can store energy in a spring or an elastic, and it ends up being represented by the same equation. It's real similar to one another. The energy stored in a stretched spring or a stretched elastic, or a compressed spring or a compressed elastic, or something like that, right? Even if you hit a rubber bumper, when you ride the bumper cars, right? So when you ride the bumper cars and you hit the wall, for a brief time, the rubber bumpers compress. It's not really an elastic or a spring, but it compresses and becomes spring potential energy. Okay? And that's what propels you backwards, right? It has the ability to do work. Yeah, it has the ability to do work because you end up bouncing back from it. Okay, a basketball, when you bounce it on the court, a basketball compresses, it squishes. As it squishes, it stores energy. It's called the elastic potential energy. Well, the basketball comes back up by itself, right? Not exactly by itself. It comes back up because it was stored energy in the basketball when it was squished, when it hit the ground. Elastic potential energy, or spring potential energy. The reason, by the way, that gravitational and elastic and spring potential energy are capitalized, and I just highlighted them, is because we're going to talk in more detail about both of those types. Gravitational potential energy today, and elastic and spring potential energy down the road in about a month. Any others? Not in the same way, but we could say nuclear would be a type of potential energy. Nuclear energy is energy that's stored in the nucleus that can be released and do work. Okay, it can power a city by generating electricity, or it can destroy a city if it's in a different context, right, in the case of a weapon. Nuclear energy. What about electrical energy? We're going to talk more about both of these in quite a bit of detail in Physics 30, not in Physics 20. We do quite a bit of electric energy, and then in our last unit in Physics 30, we do a fair bit of nuclear as well. You could even, I suppose, add solar in there. Again, not in exactly the same way, but still, it's not doing anything right now, but it has the potential to do something. We're going to focus in this unit on our kinetic energy and our gravitational potential energy. Kinetic energy, we said, is the energy of motion, and it can be described by an equation that you've probably already seen before. In fact, I know you've seen it in Science 10. EK, which is kinetic energy. Do you remember what the units are for kinetic energy? Somebody said it? It's joules. We usually just represent it by a J, though, a capital J. The equation is, I'll give you the first one to see if you recognize it here. 1/2. Now you know it, right? You guys have seen this before, haven't you? Yeah? Close. Close. What did he say? He said 1/2 of the mass times the velocity squared. It's actually not 1/2 of the mass times velocity squared. It's 1/2 of the mass times speed squared, yeah. Mass needs to be measured in kilograms, and of course that's a scalar. This is speed, not velocity. It's got to be measured in meters per second. Kinetic energy is in joules, and kinetic energy is a scalar because mass and speed are scalars. Now, gravitational potential energy, we're going to represent by the equation EP. That's gravitational potential energy. That's measured in joules as well. Do you think it would be a vector or a scalar? It's definitely a scalar. All types of energy are scalars. EP is equal to m times g times h. M is the mass, once again, and that's going to be measured in kilograms. G is We're going to say 9.81 meters per second squared. Just make it positive, but I'm putting that in quotation marks because you understand that it's 9.81 if we're here on Earth. But if you were on the moon or even on the top of Mount Everest, it would be less, right? It wouldn't be 9.81. So it's the acceleration due to gravity, the magnitude of the acceleration due to gravity, which we're going to use it. We're going to always make it 9.81 on Earth, but it can be different. And h is the height of an object in meters. Now, that height can be measured relative to whatever you want. The gravitational potential energy of this water bottle right now sitting on this desk, relative to the desk, is 0, because the height of the bottle relative to the desk is 0. But the gravitational potential energy relative to the ground is something, because the height of the water bottle relative to the ground is about 75 centimeters. So relative to the ground, it's something. Relative to the table or the desk, it's 0. Why? Well, ultimately, it has potential to fall to the ground. It doesn't have any potential to fall to the desk because it's already on the desk. Make sense? Okay, I want to do an example question with kinetic energy, and then we'll have you work on some questions. We'll leave potential energy for now. Okay, we'll do another example with potential energy after you've had a chance to work on kinetic energy questions. All right, here's our question. It says a 2,000 kilogram car has a velocity of 90 kilometers per hour to the north. Calculate the kinetic energy of the car. We're going to say that m is 2,000 kilograms. And we're going to say that v is 90.0 kilometers per hour to the north, right? To the north? Does it matter that it's north? Ernesto? No, it doesn't. Why? Because kinetic energy is a scalar, and speed is a scalar, right? I put the direction in there. That's fine, but it's completely unnecessary for this question. We don't need it at all. Now, we got to convert this to meters per second. You guys remember how to convert kilometers per hour to meters per second? What is it, Dexter? Yep. So we're going to, hold on for a second. So times it by 1,000. We get 90 times 1,000. Okay, that converts the top to meters. And then, divide it by 3,600 to convert the hours to seconds. So when we do that, we end up getting 25.0 meters per second. So let's say EK is equal to 1/2 mv squared. It's 1/2 of 2,000 times 25.0 squared. Do not put the north in there. Even if it was south, okay, if it was south, do not put the negative in there. Okay, in this equation, v will always be positive. Even if the velocity is 37 degrees north of west, I don't care. If it's 90 kilometers per hour, 37 degrees north of west, v is 90 kilometers per hour. Okay, in these questions, the direction just does not matter. Let's calculate now what that works out to be. I'm going to say 0.5 times 2,000. Don't forget to square the 25. That's a fairly common mistake, actually, forgetting to square that 25. We do this, we get 625,000 joules. Now, we're going to have to round that to how many digits? 4, 3. Final answer should be... Max, what should the final answer be? If this is 4 and this is 3, final answer should be 3 digits. Good. So we're going to say 6.25 times 10 to the what? 5, yeah. 1, 2, 3, 4, 5. 6.25 times 10 to the 5 joules. Oh, wait. To the north, right? No? Because kinetic energy is a scalar. You don't put north there. If you do, it's actually wrong. Okay, I'll take off a point for that. Not only do you not need direction for the answer, you should absolutely not have direction for the answer because it's a scalar. Doesn't make any sense to talk about energy in the context of direction. So we'll look at example number 2 up here, which requires us to do a little bit of algebra on that equation 1/2 mv squared. So let's say we want to find the speed of a 200-gram ball with the ball's kinetic energy of 6.4 joules. We've got to convert that to kilograms first. My mass is 200 grams, or 0.200 kilograms. We divide by 1,000. And my kinetic energy here is 6.40 joules. We want to find the speed of this here. So we know my equation, of course, is EK is equal to 1/2 mv squared. How do I solve for V now? Hey, how do I solve for V? I should have shown you this one before I set you to work on that worksheet. Well, we got to get rid of the half and the m, right? How do we get rid of the half and the m? Yeah, you can divide by 1/2 m. You can say EK divided by 1/2 m is equal to V squared. Does that make sense? Now, you could do this as well. I don't care which way you do it. This way works as well. You could get rid of the half by multiplying by 2. Because when you multiply by half, it's the same as dividing by 2, right? So we could multiply by 2 and say it's 2EK and then divide it by m is equal to V squared. Does that make sense, guys? Either one of those works. I don't care which way you do it. Generally, when I'm doing it on the board, I do it this way. But there's no reason in the world why you can't do it the other way. All right? Now, whichever way you end up doing it, how are you going to find V? At this point, we're almost there. Yep. Yeah, you're going to square root it, right? So we're going to say V is equal to the square root of EK over 1/2 m. Or we're going to say V is equal to the square root of 2EK over m. Either way. So this is the way that most of you guys, I think, did it. So let's do it this way. V is equal to 6.40 joules divided by 1/2 of the mass here, 0.200. Now let's square root that. Let's pull the calculator out for this. I'm going to say 6.4 divided by, now some of you are going to look at that and say, oh, 1/2 of 0.2 is 0.1, right? And then you're just going to say 6.4 divided by 0.1. That's fine. But if the numbers are a little bit more complicated on the bottom, then do this. Say 6.4 divided by bracket 0.5 times 0.2. Make sure that whatever you have multiplied on the bottom is in brackets. Does that make sense? Okay, that gives us what's inside the square root sign. We square root that, and we should get 8. And we do. 8.00, should be 3 digits here, 8.00 meters per second. Is that good? Okay, that should help you with a couple of questions on that worksheet now. All right, back to work on that worksheet. Let's go over questions 3, 4, and 5 right now. I'll leave you with the other ones to work on. 3 says, what's the speed of a 5-kilogram object that has a kinetic energy of 250 joules? The mass of the object is 5.00 kilograms, and the kinetic energy is 2.5 times 10 to the 2, or we could just say 250 joules. What's the speed? This is going to be like the second example question that we did a minute ago. We're going to say EK is equal to 1/2 mv squared, and just rearrange it to solve for V. We're going to solve for V. We have to get rid of the half and the m. How do we do that? A couple ways. Remember we just did it? What's one way? What's one way that we can get rid of the half and the m? To get rid of the half and the m first. Careful, you can't times it by 0.5. You could times it by 2, or you could divide by 1/2. So times it by 2 or divide by 0.5, either one of those. So I'm going to times it by 2 and then divide by the mass. That gives me V squared. Then I'm going to square root that to get V. So V becomes equal to 2 times 250 divided by the mass, which is 5.00. Excuse me. What do we got here? 500 divided by 5 is 100. And then the square root of 100 is 10, but it should be 10.0 meters per second. How many people got that? Right? 2,000 kilogram truck is traveling at 110 kilometers per hour. What's the truck's kinetic energy? Here's my mass. And my speed is 110 kilometers per hour, but I got to convert that to meters per second. Dexter told me the last time how to convert it to meters per second. Multiply by 1,000, divide by 8, 3,600, right? What does that work out to be? 110 times 1,000 divided by 3,600. 30.555. Okay, the kinetic energy is 1/2 of mv squared. And what does that work out to be? Other than the conversion here, this is a pretty straightforward one, right? Don't forget little things like squaring the speed, which is a fairly common mistake. But if you pay attention, you're going to get this question right. What does it work out to be? Do you have it? 9.3 times 10 to the 5. You've rounded that to 2 digits. Should it be 2 digits? Is she right? Yeah. It is 2 digits. We got 2 and 3, so the final answer is going to be 2. And number 5 says a 15-kilogram wagon travels 30 meters in 15 seconds. What's the kinetic energy? My mass is 15.0 kilograms. My distance is 30.0 meters. And my time is 15 seconds. We're going to say EK is equal to 1/2 mv squared, but we don't know what V is. Dexter, how do I find V there? Good. We're just going to say V is equal to distance divided by time. Right, so it's going to be 30.0 meters divided by 15.0 seconds, which gives me 2.0 meters per second. Good, good. Now let's sub that in. 1/2 of the mass of 15 kilograms times 2.0 squared. And that gives me 2 squared is 4, times 1/2 is 2, times 15 is 30. It's just 30, isn't it? 30.0 joules. That's purely a coincidence that it's the same number as the distance. So don't just, next time you see a question like this, don't say, oh, it's going to be the same as the distance. It's not likely going to be the same as the distance.